Everybody, my name is Christopher Collison, and we are about to embark on a journey to look into the crazy world of quantum mechanics. We'll look over how quantum mechanics is very bizarre in the next few slides. I'm going to be recommending books such as this that kind of tie in with quantum mechanics, but I'm also going to say to you, because we really need to get through the chemistry of quantum mechanics, this textbook by Donald Macquarie is excellent, and I strongly recommend that. In fact, I'm requesting that you pick up this book because it really contains all the notes for the course. Today, what we're going to talk about is one of the crazy experiments, the young slit experiment, that really tells us about how, as a subject, as an experimenter, we actually have an impact on the experiments that we're running, and we can think about that towards the end of the presentation. Welcome to the class. Let's dive straight in. So what we might note from this particular slide is that in this work we have a description of the behavior of matter and light in all its detail, but in particular what's happening really at this atomic scale. Why do we bring light in? Well, light's important in the course that we're going to be looking at. It's also going to be important for us when we think about spectroscopy and how light interacts with matter as chemists, and how we can use that interaction of light and matter to tell us about the materials that we might be synthesizing. So let's think about how at the atomic level, really, we don't have any experience with what's going on. At that atomic level, we have to start thinking about how things don't act like waves. Okay, they're not particles. They're not clouds or billiard balls, and we've heard all these things before. You know, the electron cloud. What does that mean? We have to kind of go beyond these perhaps classical level descriptions. And atoms are certainly not like weights on strings, but we're actually going to find that we're going to start with a classical view of everything before we jump into the quantum world. What is light, and how have scientists looked at light over the last few centuries? Well, Newton thought about light as particles, the corpuscular approach of Newton. Then it was discovered to be wave-like, and we know that it's wave-like in that we see all these refractive properties and diffractive properties that are considered to be wave-like. Then in the early 20th century, sort of about 100 or so years ago, we went back to thinking about light as particles. We've also considered that electrons historically are particles. We're going to find out that electrons also have wave-like properties, and we'll talk about the history of quantum mechanics, where we think about light being considered as a particle again early in the 20th century, and electrons now being considered also as wave-like. And we'll talk about de Broglie and some of the steps that were taken to introduce quantum mechanics as we go through the course. I put in here, now we have given up. This actually comes as a quote from this book in here, and this is where a large part of this particular lecture that I'm presenting today comes from, the Feynman lectures on physics. Very entertaining chapter on the craziness of the quantum world. So we haven't quite given up, but really the point here is we don't really understand what's going on, and we'll talk in a second about how I can't really explain to you what's going on, although I can tell you what's going on. But really, light and matter is neither wave nor particle. So what is it? Well, it's certainly been confusing, and there was this increasing confusion in the early 20th century, and it turns out that this confusion was resolved by Schrödinger and Heisenberg and Born. and that confusion was resolved through the development of quantum mechanics. So quantum mechanics and the work of Schrödinger and Heisenberg and Born presents us with a consistent description of matter on a small scale. It's this atomic behavior. It is peculiar, it's strange and mysterious to everyone, both to novices, so it's going to be confusing to you, and it continues to be confusing to me, and I'm very low on the scale here of theoretical physicists, but it's still confusing to theoretical physicists and chemists alike. The point here is that we all our human experience is associated with large objects, and now we're starting to think about these things on an atomic level. Very different. So we are studying a mystery. We have to learn about quantum mechanics. It's going to be really helpful to us as chemists. We're going to learn about it in an abstract way. We have to recognize it's very unusual. We have to be a little bit imaginative. We can't explain these phenomena in a classical way, and everything we've done till this point has really been about classical physics, classical physical chemistry. And as I mentioned earlier, we can't explain how quantum mechanics works. It's like the way the universe works, and we can't yet explain how the universe works or how it was made. And this is where I make these connections to the origin of the universe. We don't really know where the universe comes from or why it exists, but sometimes we can tell how it works. We can't explain where it's come from, but we can say, oh, it works like this. And that's what we're going to try to do. That's what quantum mechanics does. It sort of strips away the why, and it says, well, this is how atoms actually start to behave. So let's set some expectations for the course, and let me get this stuff off my head straight away. I think that quantum mechanics ends up being, is this the stuff of the supernatural, fate and destiny, and predicting the future? There's a great book out, very recent publication by Yuval Noah Harari, Homo Deus, and in that book he talks at some point about free thinking, free will. So I actually think that free will might exist if we allow for quantum mechanics. So then it takes us into consciousness. It's probabilistic. It's about probabilities, quantum mechanics, whereas classical physics is about directly predicting what's going to happen in the future. But I mentioned a few seconds ago consciousness and the soul, and Roger Penrose recently got the Nobel Prize. He has a wonderful book out called The Emperor's New Mind, and it's about consciousness and how quantum mechanics can tie in with consciousness. We think a lot about artificial intelligence at the moment. Is it possible to actually build consciousness in a computer? Do we need to map or match quantum mechanics and quantum computing to computing in order to do that? Do we want to do that? Lots of thoughts and mysteries. Quantum mechanics has to be included if we're going to make any progress there. As we kind of move beyond consciousness and more towards things like the soul, there are some great books out there, very spiritual books. In fact, one by Gary Zukov, The Dancing Wu Li Masters. And there's also a wonderful book, The Universe in a Single Atom, and I think sort of Buddhist ideas are really the precursors for quantum mechanics that came, 2,500 years before Schrödinger and Born started working on this stuff. In Buddhism, we ask the question, do computer circuits only exhibit two states, on and off? But what happens when you switch the computer off? There's something that is neither on nor off. And I think with quantum mechanics, we ask ourselves, is it a wave? do we have a particle, or is there something in between that we really don't understand? And I think it's the latter here. And these questions have been thrown up in Buddhism for centuries. So we might also say, what happens when reality doesn't fit the possible answers that we put forward as scientists, right? So all these things, the strangeness of quantum mechanics, the mysteries of the universe are kind of, they're included in quantum mechanics. We're not going to spend our time worrying about what we don't know. I'm going to tell you how we use quantum mechanics to help us in chemistry. But here's kind of the background of why quantum mechanics is so intriguing. So all these books are here. There's another book. There's a number of books out there. One by Brian Greene that I quite like. And this is more scientific. It's kind of less about the intrigue, but a very good layperson science book to read. If you want some sort of context behind what we're doing in the chemistry here. The rest of the presentation, I'm going to talk about this young slit experiment. So we'll go into the details of that experiment, and then from there, I'll introduce a couple of concepts. The Heisenberg uncertainty principle, for example, and we'll see these things pop up as we go along through the rest of the course. So let's start with that young slit experiment. And what I'm going to do first is say, let's imagine that we have some kind of gun in here, and this gun perhaps is maybe a short barrel. It's like a shotgun, and in principle bullets can kind of spread out all over the place here, right? So we can get bullets coming in all these different angles, and we've got a wall in here, and this wall, sort of armor plated wall, has these gaps in the wall. And so what happens is these bullets can move through these slits. And we also imagine a backstop, and this backstop here has some kind of movable detector in it. Let's imagine a small little tray of sand. So we imagine that all the bullets that pass through these slits in here, so all these bullets that pass through the slits, they're going to end up either hitting the backstop and then just sort of dropping to the floor in here. So we'll have a pile of bullets in here, so we know how many bullets have hit the backstop. That's important, actually. But we also have a movable detector that we can move kind of up and down, and we can say, well, how many bullets hit this detector as a function of this position X here away from the center, and this X is moved away from the center of the gap between the two slits. So this is our experiment, first a classical experiment. So what things, as we set ourselves up, as we tee ourselves up for the quantum mechanics experiment, in this classical experiment, what we think about is, as I've mentioned, there's large angular spread. So maybe it's a shotgun in here. We've got this wall of armor. It's got two slits just big enough to let a bullet through. The wood is this backstop, and it absorbs the bullet. We have a detector. It's really just a little thimble of sand, and it absorbs and accumulates the bullets, and that detector moves up and down. And so now we ask the question, what's the probability of a bullet hitting a certain position as a function of X away from that central position on the backstop? So the probability is the number of bullets emptied out of that detector divided by the total number of bullets that have hit the backstop. Okay, so that makes sense to us. We're also going to say these bullets are indestructible. The bullets themselves, they don't break into different chunks. So when we count a bullet, we're counting a whole bullet. There's not going to be any half bullets in there. So these bullets are indestructible. They don't break. If the gun fires at a very low rate, either a whole bullet arrives or no bullet arrives at any sort of period of time. And these bullets always arrive in identical lumps. We're going to use this word lump a few times today. The probability, by the way, is going to be predictable. What does that mean? Well, supposing I cover up hole number 2. And so when I cover up hole number 2, I find that the probability of finding a bullet here is found to be this shape, right? Most of the bullets go through at an angle, right? So as these bullets go through, we're going to expect that most of those bullets that make it through are going to hit on the back wall, this position here. There's going to be some distance x away from the central position. If I cover up hole number 1, then what I'll find is I'm going to get this probability that looks something like this, right? So it's kind of predictable when we cover up each of these slits. If I have both slits open, then I'm just going to simply sum those probabilities, and I'm going to end up getting some curve in here that looks something like this. Okay, depending on how far away those slits are will affect the peak here at the top. But the idea is we can just sum up these probabilities, and there's no interference, or that interference is going to become important later. We're also going to be thinking about a waves experiment. So it's no surprise here that we're going to be thinking about particles and waves. So we're going to think about this waves experiment. So imagine that we have a shallow trough of water with a wave source. So what does that look like? Let's try something here, and we'll click on this link. And here we go. So we have a wave generator in here and some water. We have these 2 slits, and as the waves move through these slits, each slit ends up being a point source for a successive circular pattern. And as we come back to our PowerPoint slide, what we find is, as I say, we've got this circular pattern in here, new waves, and we start to get these interference patterns that generate. If I think about these lines, by the way, the peaks of those waves. So when we have 2 peaks arriving at the same time, we've kind of doubled the height of that wave. And so we're going to get where these lines intersect, we're going to get, if we think about this and we draw a line, we're going to see a large intensity of that wave at certain points on the back of. So if we draw another one in here, we're going to see certain peaks. We're going to end up seeing an interference pattern. I won't go into that here because that's something we can pull from university physics. The point here is the detector that we're going to use. We're imagining a detector that measures the intensity of that wave motion. It turns out that the intensity is the square of the height of the wave. So what does this look like? If we go to university physics, if we cover up one hole, by the way, then what we're going to find again is we're going to see this sort of very familiar probability pattern, or this very familiar intensity pattern. But when we have both of these slits open, what we're going to find is we're going to see this interference pattern. We're going to get when a trough in a wave interferes and overlaps with a peak, then we've effectively got a zero intensity. And we see these points where we get zero intensity along the absorber here, or along the backstop. And when the peaks add on top of each other, then we're going to get these points of large intensity here. So that's the interference pattern that is apparent when we have 2 slits and we have waves that move through those slits, and those slits now act as point sources. That's very typical in university physics. So let's think about the details here for a second. So remember, a wave can have any height, and it depends on the amplitude of the source, and it depends on where we detect that wave. So there's no sort of binary effect with waves. There's no lumpiness. There's no sort of on or off approach with waves. There's a continuum of these heights. As I mentioned, the diffraction takes place at the slits. And the pattern for this intensity, when both of the slits are open, is based on this interference of the waves. Okay, it's not simply the sum of the intensity when we shut off slit 2 plus the intensity when we shut off slit 1. It's a constructive and destructive interference. And the relations for these interfering waves are based on the heights of the waves at the detector. Okay, so when we have an interference between a peak of a wave and a trough of a wave, we'll get something close to 0, and the detector can detect that height, if you will. So the result here is very different to the result that we see with the bullets. And so mathematically, we can also write in terms of intensities. We can describe the intensities mathematically, and we've got this sort of interference term in here that helps us. So we won't worry too much about the math right now. There'll be plenty of math in this course. We're going to go back to sort of some of the aspects. So there's no lumpiness, but an interference is seen. Now we're going to ask ourselves, what happens with electrons? And first of all, let's think about how this electrons experiment actually runs. And so instead of what we have in here, we have an electron gun. We have a wall that with slits in it that stops those electrons moving through unless there's a slit there. And we're going to have some kind of Geiger counter type detector in here. So let's look at those experimental details. We're going to use a hot tungsten wire. So think about a sort of old-fashioned light bulb. And electrons, this is the thermionic effect. Electrons are emitted from a very hot wire. And those electrons are accelerated by positive electrodes so that they're accelerated towards the backstop, basically. The detector that we're going to use is an electron multiplier. Think about something like a Geiger counter, and it's going to be connected to a loudspeaker. So we're going to have here these clicks. This is how this experiment was first done, and all the clicks have the same loudness, if you will, and there are no half clicks. The clicks are all the same. There are erratic clicks. What does that mean? We might have bursts of clicks that come at one, in 1 5-second period, and then the next 5-second period there are fewer clicks. But on average, we can measure this sort of average rate in here. As we move the detector, the rate changes, but as I've pointed out earlier, that single click loudness is always the same. So let's look at some more experimental details. If we reduce the temperature of the gun, right, the click rate slows. We can actually slow down the rate at which electrons move through the slits. That will become important later. But each click still sounds the same. With two different detectors, we would find that one or the other would click, but never both at once. So each electron is its own thing. It can't be detected by two different detectors. That electron can only be detected by one detector at a time. So in other words, whatever arrives at that backstop arrives in these identical lumps. So an electron is an electron when it's detected at that backstop detector. So we kind of say, all right, yeah, that makes sense. Electrons, it must be particles. They must be kind of like these bullets. It must be like the bullet experiments. So let's actually have a look at what the results of this experiment are. And of course, if we cover each hole, what we're going to find is indeed we get the very typical results. By the way, we get these results for both the wave-based experiment and for the bullet-based experiment. We get these very predictable probabilities. But what happens when we have both slits open? It turns out that we end up seeing an interference pattern. Okay, so what does that tell us? It's kind of bizarre, because if we're thinking that electrons are lumps, are like bullets, we wouldn't expect to see this interference effect. But these electrons seem to interfere with each other. So how do we understand the behavior of these electrons? So there are some follow-up experiments that we're going to look at. But it's kind of strange because, okay, at one point in time, people thought electrons, they're just these finite particles. We kind of now know that electrons have these wave-like properties as well. So they might interact as waves, but at the same time, when they hit the backstop, when they hit the detector, there's a single lump. So what's going on? So what scientists did is they said, well, okay, let's reduce the temperature. Let's get electrons to come through one at a time. Maybe, by the way, these electrons, perhaps they're interacting with each other. They're bouncing off each other, and that's what's giving us, very small. Maybe that's what's happening. They're bouncing off each other, and they're giving us this interference effect. But it turns out that even if you have one electron coming at a time, the electron interferes seemingly with itself. It gives an interference pattern here. So apparently one electron at a time, and you can tell whether that electron's coming one at a time by looking at the detector, right? Having a series of detectors in the back wall here. They come one at a time, yet we still get the interference pattern. So that's bizarre, right? First of all, we think an electron's a lump, and second, well, hang on, which slit did it go through? If it's a lump and it went through one slit, how do we get the interference pattern? What's going on? So scientists thought, maybe the electron was split in half, but again, we remind ourselves that they always arrive in lumps. A lot of experiments were done to conclude that and make sure of that, but it's true. Maybe the electrons go in complicated paths. If you read this Brian Greene book, there's a whole description on how different people have tried to set up different paths, complicated paths. No, the electrons don't go in complicated paths. It turns out the math is also quite simple, relating the probabilities of P1 and P2 going through each of the slits while covering the other one up to P1, 2. It's basically the same as the waves experiment. Okay, so the difference is that now in reviewing the results, I won't do it here, but we end up getting complex numbers. Okay, that's scary, but it turns out we're going to have to think a lot about complex numbers. They're really embedded in quantum mechanics, and we have to face that in the work that we're going to do over the next 14 weeks or so. So how do we conclude? So yes, the electrons arrive as lumps. They come through like particles. The probability, nevertheless, is distributed like wave intensity. We conclude that electrons behave sometimes like a particle and sometimes like a wave. And we're also recognizing that the amplitudes of these waves must be described by complex numbers. We'll explore that in our course. I'll take you through that. It also seems that, if we ask the question, does the electron go either through hole number 1 or through hole number 2, it seems that that's not true, because one electron at a time still gives us this interference pattern. So it must be false that either an electron goes through one slit or the other. So let's explore that a little bit more. And this is what scientists did with a follow-up experiment. What they did is they said, let's watch which slit the electron went through. So electrons scatter light. If we shine light on one of the slits, as the electron comes through, there should be a little spark, a little flash when the electron starts to interact with the light, and we can detect which hole the electron actually went through. So that's what physicists did. And what happens is when we see a small flash in hole number 2, so when the hole passes through hole number 2, I guess it's the bottom here, we'd see a flash just after that hole. Okay, when we would hear a click from the Geiger counter on the back wall, we would also see a flash. So the experimenters would also see a flash, and so they would know that the electron that gave the flash also gave a click, and the result here was that the electron either did go through hole 1 or hole 2, but never both. So experimentalists actually demonstrated those electrons would be either going through hole number 1, or slit number 1, or slit number 2. However, the crazy thing was that when they ran this experiment, the probability patterns that were observed were like with the bullets experiment. The interference pattern disappeared. So visually, what does that look like? So here we've got this light source here. So we've got this light source here, and when an electron went through hole number 2, the light and the electron would interact here. We'd see this flash at position A and here, and that would correlate to the electron actually then going on to hit the detector in here. Okay. It turns out that when that happened, the interference pattern completely changed and was removed purely by looking to see which hole the electron went through. So by us trying to find out where the electron went, we changed the outcome of the experiment. We lost the interference curve. The key here is when, people say, well, when we're looking at the electrons, by the way, we're probably disturbing them with the light, okay? They're thinking, okay, the light is coming in and it's impacting the electron. So that's the problem. That's what's destroying the interference pattern. But there are also some sort of follow-up experiments. What experimenters did then is they said, well, let's actually reduce the light source intensity. So we turn down the intensity of the light. That means you actually have fewer photons. What happened there is not every electron that hit the back screen, right? So we have our back screen with our detector in it. So not every electron that got detected at the back screen had a flash, because there are fewer photons. There were fewer photons than there were electrons, and so not everyone would give a flash. It turns out that the electrons that were seen with a flash gave these distributions that were like the bullets. And it turns out that the electrons that weren't seen gave this kind of wavy interference distribution. So the bottom line here is that if the electrons weren't seen, then we still got the interference. If they were seen, we didn't, right? And so what this kind of looks like is not so good, but you'd see this sort of interference pattern that kind of sat on top of a kind of sum of these probabilities. If you're not quite sure, if you're not following me at the moment, don't worry about it. The point here is that when we stop looking at these electrons, when we stop the act of seeing which slit they came through, they start to interfere with each other again. Scientists also said, well, hang on a second, maybe if we're using a high frequency of light, there's too much energy in there. It's impacting the electron. So scientists then say, well, let's go to lower frequencies. Lower frequencies mean higher wavelengths, and higher wavelengths are going to give us less resolution to know where that electron is. It turns out that when the frequencies went down and the wavelength went up, at that point where the wavelength was so long that we only would see a big fuzzy flash, at that point where we couldn't tell the difference whether the electron went through slit number 1 or slit number 2, at that point the interference pattern re-emerged. Pop, just like that. And so the crazy thing is, and really the conclusion to this all is that, I'm not sure if this turns up in the next slide, but basically here's the crazy part. The electron knows that we are watching it. That's the crazy part, that the electron somehow will change its behavior based on whether we're looking at it or not. Another way, maybe we might bring in some Buddhism perspectives here. So we're all connected. In Buddhism, everything is connected. We're all interdependent, and nothing acts individually on its own, separate from everything else that exists in the universe. So that idea also comes across in quantum mechanics. And the thing I would say here, we are connected, subject and object here. The electron is connected to us because when we start to look at it and observe it, it changes its behavior. That'll be a key outcome to quantum mechanics. That's why things get pretty bizarre in the world of quantum mechanics. So, a few summary statements here. It's impossible to measure which hole the electron went through and at the same time not disturb this interference pattern. Absolutely impossible. Heisenberg suggested that there are these natural laws in the universe that limit our ability to do experiments. We can't keep going smaller and smaller and smaller and start to understand what's going on. Subatomic particles and quarks, string theory becomes difficult. We have reached our limits often, and we're not always going to be able to go smaller and smaller. Heisenberg basically proposed a general principle. It's called the Heisenberg uncertainty principle. We'll talk about that in the class. That uncertainty principle is it's impossible to design an apparatus to determine which hole the electron passes through that will not at the same time disturb the electrons enough to destroy the interference pattern. Quantum mechanics, the mathematical framework that we'll develop, has to address this uncertainty principle. We're going to need a new set of mathematics to work with the uncertainty principle that is very different to the math used for classical physics. And nobody has ever yet found a way around the uncertainty principle. So all we can say is that this is a conclusion from these Feynman lectures. So I'll finish with this since I took a lot of the material from that. If we look at the holes, we can say that the electron goes through either hole 1 or hole 2. If we don't look at the holes, we can't say that an electron goes through either hole 1 or hole 2. It may go through both. It may go through neither. We can't tell. And this is a quote from Richard Feynman's book. This is the logical tightrope on which we must walk if we wish to describe nature successfully. So at the end of the day, we don't know, but we do have a mathematical process that can describe the probabilities of which slit the electron went through. We're going to come up with some mathematics that we need that is associated with probability a lot in this course. So I hope that this is an intriguing introduction to quantum mechanics. It doesn't really tell where we're going yet in the course, but I hope it kind of says there's some mystery here and there's some intrigue here. And we have to be imaginative with how we look at this. We have to manage our frustrations with the abstract nature of quantum mechanics, because that's just how it is. But I hope you enjoy and recognize that this is a gateway as a scientist to start to get your head around and recognize that quantum mechanics exists, and we have to include it if we want to move forward in our scientific research.